Hello, this is a video on summing up the four cases of the derivatives of exponents and bases. And we're going to throw in the proof of the power rule for taking the derivatives of something raised to a power in this as well. I am following James Stewart's 6th edition calculus, and this is the asterisk version of this part of the chapter on logarithms and natural logs and exponential functions and things like that. And he does it twice. First, he does it from a more kind of intuitive pre-calc approach, and then he does it from a more rigorous, I want to be a math major kind of approach. Okay, enough of that. The four cases of derivatives of exponents and bases. Case number one, the derivative of a number raised to a number, which is just a number. And the derivative of a number is 0. The derivative of a constant is 0. So a to the b is just a constant to a constant, which is a constant, which is, derivative of that is going to be 0. That's the easy one. Ah, you knew that. Okay, now here is the power rule, which I'm going to prove in a second. The derivative of a function raised to a power is the power times the function raised to the power minus 1. And of course, you do have to take the derivative of whatever's in the parentheses. If it's just an x, then it's 1, and it kind of fades into oblivion. But let's say that this x here was something complicated, I don't know, something, or even something relatively simple like x squared plus 1. But basically, you're not only going to do n function to the n minus 1, but you're also going to then have to take the derivative of what's inside. The chain rule, we call that. Okay, this is basically the power rule. Number two. Number three is what we've been doing in this in my last video, which is where we're talking about if number 2 is the power function, then number 3 could be the exponential function, where we have a constant raised to a variable. And so if you have the derivative of a constant raised to a function, the derivative is going to be, first we're going to pull this out. We're going to pull out a g of x. This is not g to the x, it's g of x. Sorry, it's a little staggered there, but it's g of x. A to the g of x, that's going to pull out of the front, and then you're going to have the derivative of whatever this function is, g prime of x, times the natural logarithm of the base. If you want a proof of this, and a general explanation, see the video right before this one. But basically, the derivative of the exponential function is going to be whatever that exponential function is times the natural logarithm of the base times the derivative of the function. Okay, number 3. Finally, number 4. What if you're trying to find the derivative of a function raised to a function? Well, use logarithmic differentiation, which I think is like 2 or 3 videos ago. If you follow the link in my description, you'll get the list of all of them, and you can follow the money, or not money, follow the trail. Okay, so these are the 4 cases of exponents and base. Derivative of a constant is 0, the power rule, the exponential rule, and then use logarithmic differentiation. And now for proof of this. You remember this from earlier in your calculus life? If n is a real number, and f of x equals x to the power of n, so you have a variable, this is a power function because it's a variable raised to a constant, then the derivative of that, f prime of x, is going to be the power times x to the power minus 1. Okay, remember that? Long ago, faraway place? That was great. Well, now we can prove it given the videos that we've just had. And here is the proof. So first of all, let's take the natural logarithm of both sides. So this is f of x is y, right? So natural logarithm of the absolute value of y, and then let's take the natural logarithm of this, natural logarithm of the absolute value of x to the n. Okay, so we've just basically taken this formula here, and we've done the natural logarithm of both sides. Well, from, I think, the previous couple videos ago, we learned that you can pull that power right out of there, this constant right out of there. And so we have n times the natural logarithm of x, as long as x does not equal 0, because just don't do that. Okay, so now let's differentiate. What is differente? I don't know what differente is. Hold on a second, that's not right. That's better. Differentiate. So we're going to use implicit differentiation. We're going to take the derivative of this and the derivative of that. which means, well, the derivative of the natural logarithm of y, we know from a previous video, is the derivative of y over y, because that's 1 over y times the derivative of whatever y is. And then the derivative of this is going to be n, the n stays put, and then the derivative of the natural logarithm is 1 over x. Okay, so there we have it. We have y prime over y equals n over x. So now we just do a little algebraic voodoo. So we have multiply both sides by y, and we get y, and n, this is still n over x, but now we've got it, you know, the y on this side. So we've got the f of x equals this. And then we know that y equals x to the n, right? So we can substitute x to the n for y. And then what is x to the n over x? It's x to the n minus 1, right? Because this is x to the 1, and in using the rules, x to the n over x to the 1 is x to the n minus 1. And so there you have it. We have proved the power rule that says that if f of x equals x to the n, then the derivative of f of x equals nx to the n minus 1. And there you have it. Quod erat demonstrandum. That which must be demonstrated has been demonstrated.